Friends, in the previous video, that is part 8, previous year's questions of CSIR-NET involving carbocation was discussed, and now I am going to discuss the questions from GATE and IIT-JAM. And for carbocation chemistry related videos, that is structure, stability, generation, fate, that you will get in the playlist link given in the description box. So let's start. The first question is saying it is related to rate of solvolysis. 5 compounds are given and we have to find the order. Now solvolysis means where the solvent itself is acting as nucleophile. So this is basically substitution, and here we have to check the carbocation stability. So rate of solvolysis is nothing but, the question is actually you have to find the stability order of carbocation, because when stability of carbocation is high, then SN1 mechanism if we consider, the rate will also be high, because carbocation generation, that is the rate determining step. So here leaving group is common. What is the nature of X, that is also given, but we don't have to bother about this X, because X is common for all. So carbocation will be generated at the position where CX bond will be broken. Now here neighboring group participation will take place, which will stabilize the carbocation. For NGP, that is for, if you want to know in detail what is NGP, you can click on the link right now appearing on the screen. And based on NGP, here if we look at the structure properly, you will see there is a 3-member ring present in the structure T. We also have 3-member ring in R. Now when we consider which group will be better neighboring group, then you have to consider this 3-member ring first, then pi bond, and then it is sigma bond. Okay, because if 3-member ring is breaking and it is taking part in NGP, obviously that is from energy point of view, if this, as it is highly strained ring, it will try to break. So that is why its cleaving tendency is very high. So NGP will be maximum from this 3-member ring. Now from that logic, T and R, these should give maximum rate of solvolysis. Now among T and R, which one will be giving more rate? That is T, because in T the ring is more strained. If you look at the structure R and T, in R there is some amount of flexibility but not in T. So that is why T will be giving higher rate. So T and R, as 3-member ring is present, it will come first, T or R, but T will come before R. And then we have double bond only in Q. So after T and R it should be Q, and then it is P and S. Now T and R, as we know, T is maximum, that you can find only in option A. TR, then Q, and then SP. So here this is the option A based on this explanation. But if we want to see the structure, so this positive charge, it is basically carbocation that you will be getting from T. Now if this ring is broken, it is now migrating here, another carbocation. But basically you have to consider this average structure, which is non-classical type of carbocation. Here over 3 carbon center, the electron is as if that is delocalized. Fine. So this is the average structure. And for non-classical carbocation, there is also, I have made a video which you will get in the playlist link. Fine. So this is the carbocation generated from T, and then this is the carbocation which will be generated from this one, that is S, right? So here this CC bond, it is breaking and it is making a new sigma bond, but you have to consider this average structure. Here sigma bond is the NGP. And then if you consider this Q, from Q you will be getting this carbocation at this position. Here pi bond will be taking part in neighboring group participation. So this is the average structure where over 3 carbon electron is delocalized. So option A is the correct option. Major products P and Q formed in the reaction given below. So from the first one, we will be getting P in presence of silver oxide. In the second case, we will be getting Q. So in presence of silver oxide, which is source of Ag+, this Br, it will be forming AgBr. That means you will get a positive charge at the position where Br is present. So if I am writing this positive charge here, now we have O and H and methyl group. So this is, we are getting from the first one, and from the second one, what type of carbocation will be getting? Actually it is same, only the Br is Axial in case of first compound, it is equatorial in the second compound. Methyl as it is. Now we have to basically check that with respect to this Br, here hydrogen it is in anti position, so that hydrogen will be migrating at the positive charge. So this OH bond will be broken and this hydrogen it will be migrating in the form of hydride. So as a result, now we will be getting C double bond O at this position. So it will be C double bond O and methyl group. And here in the second case, with respect to this Br, this CC bond is actually anti. So that is why it will be migrating. So OH bond is broken as usual, then this bond will be migrating here. Now we will get a 5-membered ring. Okay, and there will be CHO, methyl as it is. So this is the structure of Q and this is P. This is the structure of Q. So P, actually see, if you sure about the structure of P, then also you can choose option C. And Q, it is only present in option C. So option C is the correct option. It is diene phenol rearrangement. So diene, 2 double bonds present in this system, and there is C double bond 2. Now the same question, almost same question, in the previous video if you check from CSIR-NET, which year I cannot remember, but same type of problem you will also see there. So this is diene phenol rearrangement. From diene, in presence of this H plus, it will be converted to phenol system. So phenol system you can get in option A, option B and D, in all these options, but not here, right? So if you want to see in general what happens in this case, so this is diene system, 2 CC double bond, 1 C double bond O. In presence of H plus, oxygen will be protonated. Now once it is protonated, this double bond can be shifted here and one of this R group will be migrating at this position. So we are getting a new CC bond here. Oxygen is now neutral, positive charge will be here because R is already migrating. Here 2 R groups are same, but depending if it is different, that R group will be migrating, which is having more migrating capability. So finally we are getting this type of phenol structure because this hydrogen ultimately it will be removed as H plus and you will get CC double bond. So this that is with respect to this C double bond O, at 4 position we have this methyl group and we have this CC bond, which is part of another cyclohexane ring. Now obviously cyclohexane ring is intact in all the options. So this methyl group will be migrating at this position, which is meta with respect to C double bond O. See, this position is meta with respect to C double bond O. So just you don't have to bother about rest of the structure, just focus on this part. So methyl will be migrating here. And the relative position of this methyl and C double bond O, that will not change. So see, it is not changed here. Here also it is not changed. But what is the difference? Here methyl group that will be at meta position. So we will cancel this one because it is not in meta position. And what about this structure? So last one is also not possible because here there is CC double bond, which is not possible. So option A is the correct option. Okay. Similar type of question you can get in GATE 2011 also. So this is simpler compared to the previous one. Now same thing. So see, at 4 position with respect to this C double bond O, so this methyl group will be coming here. So if it is so, then which structure is correct? Relative position of this C double bond O and methyl will not change. So see, it is fine. Here it is not present. Here also not present. Not. So option A is the correct option. Fine. Diene phenol rearrangement. Major product formed in the reaction given below. So here we have at 1 and 2 position OH group. So this is a particular rearrangement. Remember, it is pinnacle type of rearrangement. So in this case, what happens if we want to see with this simple structure? First, here all the R groups are same, but you have to protonate that OH where it is the carbocation that will be generated after removal of H2O, that carbocation should be stable. But here all the groups are same. So if you are generating here Me2COH, So this is CMe2. There is a positive charge at this position because after protonation OH2 is removed. So carbocation will be generated at this position. Though here all the groups are same. So when this OH bond is broken, one of this methyl group that will be migrating. So finally you are getting methyl C double bond O and CMe3, which is this structure, pinacolon. But in our case, here we have all the 4 groups different. So what to do? First make it simple. Suppose this is R1, this is R2, R3 and R4. All the groups are different. But I will write it like this. Directly I am writing here positive charge. Why? Because this side only positive charge will be generated. Here we have 4 position OMe, that is OMe substituted phenyl ring, and we have phenyl ring here. But if you look at the left hand side, here we have electron withdrawing group. So obviously positive charge will be more stable here. And finally there will be migration of one of this group, R1 or R2. But which one will be migrating? Obviously the methyl substituted benzene ring, it is more donating. So that is why R2 will be migrating. So finally what we are getting, R1, C double bond O, and here we have R3, R4, R2. I have already mentioned what is R2, R3, R4. So only this NO2 substituted phenyl ring will be on the one side and all the 3 groups will be in the other side. So option A is matching, right? Okay. We have primary amine and condition given NaNO2 aqueous HCl. So this condition, very low temperature, what is will be generated first? It will be nitrous acid that will be generated, and whenever we have primary amine, suppose I am writing in general RNH2, in presence of HNO2 it will produce RN2 plus diazonium R. So when N2 is removed, which is very stable living group, because N2 is removed as a neutral molecule, now there will be positive charge. So if I am, that is in position of NH2, just imagine there will be N2, but when I am removing that N2, what I will be getting? I will be getting a CH2 plus, right? Now I will do numbering because now bond migration will be there. So this is suppose 1, 2, 3, 4, 5, 6. Now this is symmetrical type of structure. You can break any of this bond. So suppose I am breaking 2,6 bond. So if I am breaking 2,6 bond, now there will be a generation of 6-member ring. 4 and 5 there is no change. It is a junction 2 carbon. Then it is 3. 2,6 bond broken. So after 3 I will write 2 and after 2 it will be 1. But remember at 2 position there will be positive charge. And 2,6 broken, 1,6 formed. So this is 6. So finally as it is aqueous HCl there will be water and water will be attacking at this position. So finally what you are getting? You are getting OH group at this position, right? So which structure will be correct? Option D is the correct option. Okay. Rate of solubilisis, total 4 compounds are given here. So rate of solubilisis means you just have to consider the corresponding carbocation after removal of the leaving group, because based on carbocation stability we can also understand what will be the rate of solubilisis. So from the first structure, the positive charge that will be generated, it is at the bridgehead position, right? From the second one, this is the positive charge. From the third one, this is the positive charge, and from the last one, this is the positive charge. Okay. Now here if you consider stability of carbocation, then this one is basically aromatic and this is anti-aromatic, because it is following 4n plus 2 total number of pi electron, where n value is 0, so total 2 electron present in this single double bond, and here we have total 4 electron, it is following 4n. So this is aromatic and anti-aromatic. Now aromatic you have to give priority with respect to whether there is hyperconjugation or resonance. Aromaticity will always get priority. So that is why this will be showing maximum stability, this will be showing minimum stability, because anti-aromatic is very, very unstable. Now if this is 3, so 3 will be showing maximum, it will be at maximum position, 4 will be at last. So based on these, 3 at first, 4 at last, that is matching with option B as well as option C. But what about this 1 and 2 carbocation? So basically 2 will be more stable compared to this, because here planarity achievement is not possible. But in this case, because of this rearrangement, CC double bond, it will take part in this, that is the positive charge, it will be delocalized. So that is why first 3, then it is 2, 1 and then 4, option C is the correct option. Okay. Correct order of stability, carbocation, it is directly asking the question, not in the form of rate of solubilisis. Here, the first carbocation, you can see it is benzylic carbocation. So, resonance with the phenyl ring is possible, and we also have 2 methyl group, that means alpha hydrogen hyperconjugation, total 6 alpha hydrogen, that is also possible. So, this will be showing maximum stability, and which will be minimum. This will be minimum because their planarity achievement is not possible. So 1 at first, 2 at last, that you can get in option C only. So option C is basically the correct option. But why in option 3 is coming first with respect to 4. Now here we have total 3 methyl groups, so total 9 alpha hydrogen, hyperconjugation possible. Here resonance is possible. But though resonance we give more importance, more priority, but still as there are total 9 hyper conjugable hydrogens, so it will be showing more stability. Okay, so option C is the correct option. Here we have total 3 steps. We are having a carbonyl compound. The first reagent TiCl3 zinc copper couple. Now this reagent is the reagent for McMurray coupling. So McMurray coupling, it happens in presence of this type of titanium salt, TiCl2 or TiCl4, and there should be a presence of reducing agent. Here zinc copper couple is given, any other reducing agent as mentioned here, that is also possible. So we have 2 carbonyl compound. Here C double bond O, this bond will be broken, and this side is coming from one carbonyl compound, another side is also coming from the same compound. So newly generated CC bond is there. So if you apply the same thing for the compound given, what structure we will get? We will get C double bond O like this. So this is the structure which we are getting after the application of first reagent. Next we are applying cold alkaline KMnO4. CC double bond, cold alkaline condition KMnO4. So there will be dihydroxylation. OH, OH. Fine. And then finally we have H2SO4. So here OH2, it will be protonated, it is symmetrical, you don't have to worry which OH you have to consider. So this is binacol-pinacolon type of rearrangement. And finally this OH bond will be broken, there will be a CC bond at this position, and this CC bond will be migrating. So if I am numbering, it is 1, 2, 3, 4, 5, 6. Now 3-1 bond will be formed, and there will be a 5-membered ring. So this is a spiro type of compound. Fine. So this is 1. At 2 position there will be C double bond O. 2-3 bond broken. 3, 4, 5, 6. This is 2. Okay. So we are getting a newly generated 6-membered ring, and this is a spiro type of compound. It is matching with which option? It is matching C. It is very close to this 2 structure, but C double bond O is present in the 6-membered ring, not 5-membered ring. So in option B it is present in 5-membered ring, but here it is in the 6-membered ring. So option D should be the correct option. Which on reaction with NaNO2HCl, which is basically generating HNO2. Which of the following amino alcohol or alcohols, it may be more than one answer correct, will yield compound P? In compound P we have CHO group, and in all the options we have, it is amino alcohol, that means NH2 group and OH group, that is present at 1 position and 2 position. But what is the difference? The difference is, here it is axial equatorial, equatorial, axial, equatorial. Now when it is axial equatorial at 1 and 2 position, it means it is cis. This is trans. This is also trans. Equatorial one is more stable, but these two are trans. Otherwise, all the compounds, same type of substitution there. So this question, similar type of question is also we have GATE 2010, where this trans amino alcohol given. Only difference here, we do not have this tertiary butyl group, but otherwise this is trans. Now whether it is EE trans or AA trans, that is not mentioned clearly. In presence of HNO2, same reagent, NaNO2HCl, X structure we have to find, the major product X. Now these two questions are basically similar type. So what I will do, I will take the 4 molecules given in the first question, A, B, C, D, and when we apply the reagent HNO2, what will happen? We will try to see that. So this is Tiffany-Demjan of rearrangement. This rearrangement not only for this substrate, the substrate may vary. So in this case, we will see what is happening. So NH2, this position, there will be first N2 plus generation. So N2 plus, you can also remove N2, you can directly write positive charge. But I am writing here N2 plus. And we have OH group. For simplicity, I am writing R. Same type of, if we write here, it is N2 plus. I am not changing the stereochemistry because that will not change. OH, here we have R group. Then we have N2 plus, OH, R. This is axial. This is also axial. So here cis trans, if we see, this is cis trans, cis trans. So what happens when the first cis, if we take, here with respect to this N2, this hydrogen is anti. So this OH bond will be broken and this H, that will be migrating here. See, same type of problem we have also solved today, where instead of NH2 we have Br and the reagent was Ag2O. There also it is carbocation. Just removal of Br, there is carbocation. In this case, after removal of nitrogen molecule, there will be positive charge. So this is the position where positive charge will be generated. So this Cn and this CH anti to each other. So this hydrogen you have to shift in the form of hydride. So what we are getting? We are getting C double bond at this position, R group as it is. Next structure, which is trans. Now with respect to this cis N bond, this is the trans. So that is why now after OH bond breaking and C double bond O will be produced and this CC bond will be migrating at this carbon. So now CC bond is broken, that is why there will be formation of 5-member ring, and this carbon along with this C double bond O, it will be now formal group. Fine. Next structure, which is also cis, but now it is another variety, that is OH is axial, NH2 is equatorial. With respect to this Cn, now this is trans. So it is just like the structure B, same type. So same compound you will get, whether it is B or C. And from the last one, with respect to this Cn, this bond is directly anti. So now epoxidation will be taking place. Okay. So from both B and C we are getting this. Go to the previous problem. So it is asking that these compounds, these tertiary butyl and CHO, they are meta with respect to each other. So that you are getting from both B and C. So B and C, both are correct options. And what about this question, GATE 2010? When it is trans, basically you have E variety and you have A variety. Now you have to find major product. Now which one you will consider? Obviously this one, not this one. Equatorial, that is more stable. So equatorial, it is giving which structure? Basically this is equatorial, this is axial, and from equatorial you are getting this product. Meta position, R and, sorry, not meta position, 1,3 position. It is not benzene ring. Fine. So correct option should be this one, that is option B. And here we have basically do not have any tertiary butyl group, and that is why no options is also there. This is the only possibility. So option B is the correct option. Look at the structure. It is again 1 and 2 position OH group. So it is pinacolon type of rearrangement. Now which OH you will remove in the form of water? That OH where positive charge will be stable. Now positive charge will be stable towards the right hand side, because here you have two pH groups. So with respect to both pH group, this is benzylic position, so this positive charge is very stable. And finally there will be ring expansion. This OH bond will be broken, C double bond O formed, and this CC bond will be migrating here. If I am numbering 1 2 3 4 5 6 7, so now you will be getting a 7 member ring, right? So suppose this is position 2, there is a bond 2-7 bond broken, 1 position 2 pH group and 7-1 bond formed. This is 3 4 5 6, so 7 member ring where at 1 and 2 position carbonyl group and 2 pH. So option B is the correct option. This is the last question. Correct order of stability of the following carbocation. It is very easy. See here, planarity you can achieve, but not in 1 and 2. So obviously 2 you have to give priority. Now 2 at first position, that you can get in option and D and A. So it will not help. Further you have to check which one is more stable between 1 and 3. In case of 3, here more flexibility is possible, because here we have 2 carbon. This part is common, right? But if you see this part, here you have only 1 carbon, here you have 2 carbon, so more flexibility possible. So it cannot achieve planarity, but it can be close to planarity. So that is why first 2, then 3 and then 1. This should be the correct order of stability, that is option D. Okay. So that's all for today. If you find it helpful, please like, share and subscribe. I'll meet you in the next video. Thank you for your time.